Hello again, chemistry students. Today we're going to continue our topic on acids and bases, and we're going to be looking today at the very important concept of pH. And so I hope that you guys have a scientific calculator, or at least one that has a log button, because we'll be using that in order to solve these types of problems. So today, what we're going to be doing, we're first going to be defining what are pH and pOH. So I'll give you guys the two equations for each of these. How are these then related to what is known as the ion product constant for water? So we need to define what that is and why this happens. And then we'll also see how we can solve problems that involve pH and pOH. And so we have just a couple vocab words. We'll go ahead and then get started. All right. For this section, we are going to be looking at the Arrhenius model of acids and bases. And so if you remember, the Arrhenius model states that acids produce hydrogen ions, which are H plus ions, and bases produce hydroxide ions, which are OH minus. If you put the H and the OH together, you end up with H2O, which of course is our good friend water. And so typically, pure water has a neutral pH. And so it's neutral because it has the same amount of acid as it does base. So water would normally have the same amount of hydrogen ion concentration as it does hydroxide ion concentration. I'm going to show you guys a reaction that occurs every so often. Notice we have two water molecules. This water molecule is going to act as an acid, and this one therefore is going to act as a base, because according to the Bronsted-Lowry model of an acid and base, the Bronsted-Lowry acid donates a proton, and the Bronsted-Lowry base actually takes it up. And so we can see that we form two different ions. We have, of course, the OH minus ion, which is the hydroxide ion. We also end up forming a new type of ion called H3O plus, and so this is known as a hydronium ion. And so I do want to point out a couple things. Notice that this reaction is reversible. So notice that there are two arrows. One goes in this direction and the other goes in the opposite direction. And so these two can react to form these products, or these two can come back together to form two water molecules. I also wanted to point out, notice that the charges balance on both sides and that it adds up to 0. So notice that both water here has a charge of 0. If we were to take the -1 charge here and add 1 to it, we would also end up getting 0. This breakdown of water to form these two ions, we can express this using a specific constant called the ion product constant for water. And so it gets its own special symbol, capital K, which stands for constant, kind of like Mario Kart, they use K for some reason. And then the subscript W refers to the fact that this is water. And so this is the value of the equilibrium constant expression for the self-ionization of water. So this process to go here, this is known as the ionization of water. And so what we can say, this constant, which is K sub W, if we take the hydrogen ion concentration and multiply by the hydroxide ion concentration, notice that these are both in square brackets. The square brackets indicate concentration, and more specifically, they indicate molarity. And so if you guys remember from the last chapter, molarity is moles of solute divided by liters of solution. And so for this chapter, all the concentrations are going to be measured in accordance to molarity. And so remember, we use a capital M, molar, to symbolize molarity. And so for normal water, the hydrogen ion concentration is 1.0 times 10 to the minus 7. The hydroxide ion concentration is also the same because, remember, under normal conditions, water should be neutral. So these numbers should be the same. And so when we're multiplying exponents together, what we're actually doing is we're adding up. So we have a -7 plus another -7 gives us a -14. So the ion product constant for water is 1.0 times 10 to the minus 14, and that's it. Notice that because this is a constant, this number will always be that. So you will not have to worry about that changing. Also, this number would be provided to you on the test, and therefore you would not have to memorize it. Why we have this? We can use this value to go from either the hydrogen ion concentration or the hydroxide ion concentration if we know one of these. And so we can rearrange the equation and we can use this ion product constant for water to therefore calculate the other type of concentration. And so I'm going to go ahead and do a problem that involves that right now. All right, I want to remind you again, we are talking, of course, about acids and bases. Acids, as you remember, have a high concentration of hydrogen ions, which are H+, and also have a low pH. And so I'll explain why that is in just a second. Bases, which are sometimes referred as alkalis, same word, these have a high concentration of OH-, hydroxide ions, and therefore their pH is high. And so it's backwards, and the reason it's backwards is because there's a sign change. And so I'll show you the equations for that in just a second. All right, here's a problem. We're told that the ion concentration of an aqueous solution, so again, whenever you hear the word aqueous, you should of course think of water. And so for all these problems, the solvent is going to be water. We're told that the ion concentration for this, the H+ ion concentration is 1.0 times 10 to the minus 5 molar. So again, we're using molarity, and we will always be using molarity in this chapter. There are two questions. The first, what is the hydroxide concentration? And then, is the solution acidic, basic, or neutral? So I'm going to turn your attention over to the board here. All right. I apologize for the glare. I will show you what's up on here on the board. Remember that in this problem, we're told that the hydrogen ion concentration is 1.0 times 10 to the minus 5 molar. Remember that we can calculate the K sub W, the ion product constant for water, by multiplying the hydrogen ion concentration times the hydroxide ion concentration. Notice that in this problem, we're looking for OH-, and so I can rearrange this equation to solve for OH-. This is going to be equal to the ion product constant of water on top divided by the hydrogen ion concentration. All right. Remember that we're told that the hydrogen ion concentration is this. We can solve, therefore, for the OH- concentration, the hydroxide ion concentration. The K sub W is a constant. It will never change. It is always going to be equal to 1.0 times 10 to the minus 14. We plug this in down here. When we're dividing exponents, what we're really doing is subtracting. We're going to take negative 14 and subtract negative 5, which actually means we're adding 5. Negative 14 plus 5 is negative 9, and therefore the hydroxide ion concentration 1.0 times 10 to the negative 9 molar. And so we know then that this is an acidic solution because the hydrogen ion concentration is less than 1.0 times 10 to the minus 7. And so if it was greater than this value, it would be basic. If it equaled this value, it would therefore be neutral. And so this would be how you would solve a problem like this, where you might see a problem or two like this on the upcoming test. All right, let us now talk a little bit more about what pH is. All right, this is a scale that shows different everyday objects and what their pH values are. And so we have the low pHs over here, pH 7 is neutral, and we have the high pHs here. Notice that in order to calculate pH, we have to use the concept of the logarithm. And so for those of you who had Algebra 2, you will know that a logarithm is based upon orders of 10. And so every step you go up or go down is not just 1, it's actually 10. And so, which is also kind of reminiscent of the metric system, which is used by scientists. And so we're going to define pH as equal to the negative log of the hydrogen ion concentration. And so this is the reason why if you have a high concentration H+, the pH actually goes down because of this pesky negative sign here. So that confuses some students sometimes. And so remember that as acidity goes up, the pH actually goes down. And so you'll notice then things like battery acid, hydrochloric acid, vinegar, these things are acidic, and notice that their pH values are very low. We can then also calculate the related concept of pOH, very similar to the pH equation. This time it's going to be equal to the negative log of the hydroxide ion concentration. And so this is going to be dependent upon the hydroxide ion concentration. And so for things over here, notice we have things like ammonia, we have bleach, we have drain cleaner. Remember that as we talked about before, bases are typically used in cleaning products, whereas acids here are typically found in foods or beverages that we consume. All right. Also want to point out another very useful, handy equation. If you were to add the pH of any solution plus its pOH, you will always add an equal 14. And so this 14, if you remember, comes from the ion product constant for water. Remember that was 1.0 times 10 to the minus 14. So again, we see 14. And so the reason that pH of 7 is neutral is because it falls halfway in between 0 and 14. So halfway between 0 and 14 is 7, and therefore neutral solutions will have a pH of 7. And so acidic solutions, pH is less than 7, so down here. Basic solutions, pH is greater than 7, up here. And then right here in the very middle, we have our neutral solutions where the pH is equal to 7. All right, let us go through a problem that involves solving for both pH and pOH. Right. Here we have common everyday ammonia, which again, as you remember, is used in cleaning products. It contains a solution of ammonia gas, and we're told that the hydroxide ion concentration is 4.0 times 10 to the negative 3 molar. So again, remember, all the concentrations in this chapter are expressed as molarity. And so the questions here calculate the pOH and the pH of this cleaner. And so I'm going to go ahead and return. All right. I apologize. It's a little hard to see this, so I'll go ahead and I will tell you what it says because of the glare as well. We have, again, our OH. Sorry, guys, hold on. Thank you. All right, that's better. All right, our hydroxide ion concentration is equal to 4.0 times 10 to the minus third molar. We know from the definition that pOH is equal to the negative log of the hydroxide ion concentration. We simply plug this value in to this equation. We take the log of that and we change the sign. So I'm going to go ahead and take out my calculator. And so I'm going to take the negative log of 4.0 e negative 3. So if you guys remember, you have to use the E button, which is here, to then do scientific notation. We get this answer, and so typically we'll round it off to the tenths place for pH or pOH. And so we calculated then that the pOH is going to be 2.4. All right. Next, what we need to do to find the pH, we remember that if we add the pH plus the pOH, we end up getting 14. And so we can rearrange this equation so we can say that pH is equal to 14 minus pOH. So we just take 14 minus 2.4, and we end up getting 11.6. And so The answers for this problem, the pOH for this bleach or this ammonia solution is 2.4. The pH is 11.6. Notice because the pH is greater than 7, this is a basic solution, which again is what most cleaning products are. All right, and so with that, we're going to go ahead and stop for the day. Go ahead and do the problems that are assigned on RedWeb. And so we have just one more topic to discuss on our topic on acids and bases. And so hope you guys have a good rest of your day, and I will see you again soon.